I made a copy error from my notes. In class, I had written that the vector 713 was not in the span of these three vectors. I had failed to copy the minus sign from my notes. And then when I wrote down the linear system, I wrote the linear system down based on the vectors I'd just written on the board, which means that I wrote down a plus here instead of a minus. And it turns out everything after that point was correct. But in your notes, this should be a minus, this should be a minus. Somebody posted to Piazza yesterday because they were working through the lecture video from last week and couldn't get the subsequent calculations. In general, if I make a mistake in class, please let me know. Although that said, the only way to have spot this particular mistake was to do the substitution that led then to the next two equations, and I don't think anyone had time to do that in class. Okay, so we want to finish up section 1.4, which is projections and minimum distance, and start section 1.5, which is the curl and the and volumes, using the curl to compute volumes. So let me do one more example from projections and minimum distance. And so to remind you, to compute a projection, you need two vectors. One to project, and one to project onto. So you might have two vectors. You have the vector y and the vector x. And what you are doing is you are projecting the vector y onto the vector x. So you could imagine that you've got the sun over here and it's shining, and the sunlight is going like this, and it is casting a shadow. The projection, this is a right angle, and this vector right here is the projection of y onto x. Once you have found this, you can subtract it off and get this vector. This is the vector that we denote perp y x. So the projection of y onto the projection of y perpendicular to x. So you're given y and x. They live in some plane. You have two vectors. They live in a plane. And within that plane, you find two new vectors, this one and that one. And this vector is collinear with the vector x. This vector is perpendicular to the vector x. And if you add these two puppies up, you get your original y. So that was what we did. And I derived the formula in two different ways. So there was a geometric derivation, there was an algebraic derivation, but one way or another, the projection of y onto x is equal to y dot x divided by x dot x. That's a number multiplied by the vector x. So for sure, this thing is collinear with the vector x, because this thing is some stupid number times the vector x. So it's totally collinear, just like in the picture. Once you have this thing, you then define the projection of y perpendicular to x. This is simply, by definition, y minus the projection of y onto x. Okay. So let's do an example. So this is from the conceptual portion of the problems. So exercise. So let u be the vector 1, 1, minus 1, and x be the vector 2, 5, 3. So we have two vectors in R3. And you're asked to show that if you first project x onto the perpendicular part, if you first project x perpendicular to u, so here I take the vector x and I project it perpendicular to u, and then I project that resulting thing onto u, that I get, well, let's see, what should I get? So I'll do this in 2 dimensions. So here is x, here is u. The first thing I compute is the projection perpendicular to u. So that is this vector here. So it is, that's like that, and that's a right angle. So first I compute this. That's this thing right here. And then I take this vector and I project it onto u. What should I get? The 0 vector. So let's just show that this is true. It should happen if anything makes sense. So step 1, compute the projection onto the perpendicular, the projection of x that is perpendicular to u. So this means first I have to compute the projection of x onto u, and then the projection of x that is perpendicular to u is equal to x minus the thing I just computed. So that's how I'm going to do the first step. Once I've computed this, I go to step 2, which is to project this thing onto u. So first, I have to compute the projection of x onto u. So the projection of x onto u is x dot u over u dot u in the direction u. So x dot u, I have 2 plus 5 minus 3. 2 plus 5 minus 3 in the numerator. In the denominator, I have 1 plus 1 plus 1, because 1 squared is 1, 1 squared is 1, and minus 1 squared is 1, and I'm adding up all of those. And then this is all in the direction 1, 1, minus 1. So 2 plus 5 is 7, minus 3 is 4, so I have 4/3, 1, 1, 1. So I've just done this. Now I compute the projection of x perpendicular to u by subtracting this thing from x. Sorry, what? Thank you. I think at this point I've had enough problems with negative signs that I need to give you the standard warning on vector and matrix notation. So I have graded so many linear algebra exams over the years and seen the following mistake so many times. So some students write their vectors and their matrices with square brackets, and some students write them with curved brackets. And students who write it in this way often make the following mistake. So they'll start, and I don't know why they do this, but they don't do it in a continuous line. They do it like this: 1, 2, 3, 1, and then they do do da 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 da. Then to the next line, they go 1, 2, like that, 1. And then they do some more stuff. And then, next thing they know, this thing has migrated in and become a minus. And it's this very odd thing simply because they do a square bracket instead of a curved one. And they do a square bracket not with a continuous motion, but with 3. And that has led so often to migrating things that go into minus signs. It sounds incredibly daft, but it's real, and I see it, and it makes me sad. And either use curved brackets, or if you do square brackets, do it in a fluid motion so that you can't have negative signs appearing out of nowhere. Here, I lost my negative sign. I have no excuse. OK, so now I just need to project u x perpendicular to u. So that's perp u x is equal to x minus projection of x onto u. So that is x is 253 minus 4/3 1, 1, minus 1. So 2 minus 4/3 is 6 minus 4/3. 6/3 minus 4/3 is 2/3. 5 minus 4/3 is 15/3. Minus 4/3 is 11/3. 9/3 plus 4/3 is 13/3. OK, now at this point I can check. I can check that I didn't make an arithmetic mistake by checking that this thing is actually perpendicular, orthogonal to 1, 1, 1. These add up to that. So far I don't appear to have made a mistake. Now I'm at step 2. So we were asked to compute the projection onto u of this thing. So the projection onto u of the projection of x perpendicular to u. So to compute that, I just need the dot product of this. So 2/3, 11/3, 13/3, dot producted with u. So that was 1, 1, minus 1. 1, 1, minus 1. Dot producted 1, 1, minus 1. And then this was in the direction u, 1, 1, minus 1. And what does that numerator equal? 0. 0 times 1, 1, minus 1 is the 0 vector. OK. So it's true. It's true that if you first project perpendicularly and then you project onto, you get the 0 vector. Similarly, if you projected onto u and then projected that resulting thing perpendicular to u, what would you expect to get? The 0 vector. So let's actually, the second part of the question, because this is one of the conceptual questions, was prove that this is true in general, not just with these two vectors. And it's not even an R3 thing. Prove that this is true in general. So, and of course the book, so show that for any x and u in Rn, that if you project onto the perpendicular and then project onto, that you get the 0 vector. And then similarly, I won't do it in class, but you can do it at home. OK, so let's just do this algebraically. So we'll do this one. So step 1. Perp u of x is equal to x minus the projection onto u of x. Why is that true? This is how we found first we project x onto u, then we subtract from x. This was the definition. So so this is the thing inside. So now the projection onto u of perp u of x. Well, actually, let me do one more line here before I keep going. So this is x minus x dot u over u dot u times u. Okay. Step 2. I want to compute the projection onto u of the projection perpendicular to u of x. So that means I want to project x minus x dot u over u dot u times u onto the vector u. So all I did was I just said what this is. This is, so I take the vector that I want to project. So it's this long, messy thing. So I take the vector that I want to project. I dot product it with the vector that I'm projecting onto. I divide by the length of that vector squared, and I multiply by the vector. So all I've done here is use the definition of project. So at this point, I've gotten as far as I can with definitions. I have to actually do something. So staring at this, what should I do? Distribute the dot product. When the dot product of one vector with the sum of two vectors is the sum of the dot products. So this is a vector minus a vector dotted with u. So this dot product is going to be that dot product minus that dot product. And I know this is some stupid number, so that stupid number is going to come out of the dot product, and I end up with x dot u minus x dot u over u dot u times u dot u all over u dot u times the vector u. So to do that more slowly, I had this dot product went here, minus went here. I had this vector dot producted with u. This is some number, so that number came out, and I was left with u dot u. So what does that numerator equal? 0. So this is equal to 0 times u is the 0 vector. So now, in the privacy of your own homes, you should repeat the argument and see that if you first project onto u and then project on perpendicular to u, that you also get the 0 vector. It's just telling you that the reason that I wanted to do this is this can seem like just some algebraic formula, but you have a geometric intuition about projecting onto something, projecting perpendicular to something. If your geometric intuition is correct, then the algebraic stuff, which is the left-hand side, should actually, that those two things should be true. So this is demonstrating that the algebraic thing is actually geometrically sensible in all dimensions. Are there questions? Yes?
How is the numerator 0?
Why is the numerator equal to 0? Because u dot u is here and u dot u is here. And so this cancels with that, and that leaves me with x dot u minus x dot u. Are there questions? Yes?
I think exams or midterms, we have to write out the words.
Okay, so the question was, do you have to write as much as I write? You need to learn how to write, and you need to become comfortable with writing. And the reason that so why did I write what I wrote? This is the thing that I was asked to do. And when I go from this sentence to this sentence, this is actually, I'm explaining my logic to you. I'm explaining my problem solving to you. I'm taking this, which is what you asked me to do. Imagine it's an exam. I've been asked to do this. When I go from here to here, what I'm doing is I'm revealing my logic. And so the first step when I did this is I wrote out what this is. And then the next thing is this. And so the process of writing it out is the process of actually solving the problem. And one reason why you would want to actually write out what you're thinking is because if you actually make some arithmetic mistake, at least the grader knows that you were barking up the right tree. And so here, you'll see me do this quite often. I'll start with something that looks really confusing, and then I'll slowly unpack it and unpack it and unpack it until finally you have something that you can actually do. And this process of unpacking is the process of solving the problem, of rewriting it, simplifying it until you have something you can do. And that is ultimately what you want to be able to explain to someone. You don't have to, this is actually, I think, a reasonable thing to write on an exam. This is not as wordy as some of the stuff that I write elsewhere. But in general, you need to learn how to write because it's one of the big, if you cannot explain what you're doing either verbally or explain what you're doing in writing, there's a real chance that you don't actually know what you're doing. And in the process of explaining it, you figure out if you do actually know what you're doing. And ultimately, as engineers, you need to be able to demonstrate you know what you're doing. You need to actually know what you're doing, first of all. And then you need to be able to demonstrate that you know what you're doing. It's a long uphill road, but by the end of your 4 years here, you need to be able to read and write, read with great comfort and write with fluency, because without that, you're going to be hobbled in life. Okay, so we're now moving on to the other thing that we do with vectors, which is we compute cross products. Now, cross products, I believe you've seen somewhere, but you're going to be reminded of them anyway. So this is section 1.5, cross products and volumes. So let me remind you of dot products. Dot products. So if I give you two vectors in R10, can you give me their dot product? Yes. If I give you a vector in R5 and a vector in R7, can you give me its dot product? No. So dot products, they take two vectors in Rn and they give you a vector, a number, a scalar. So takes two vectors in Rn and gives you a scalar. And it has nice properties. U dot v is equal to the length of u times the length of v times cos theta. So they're useful in that they help you project onto things and figure out if things are orthogonal and so on and so forth. They have some other nice properties like u dot v and v dot u. How are they related? They're equal. Now, cross products take two vectors in R3 and gives you a vector in R3. Now, only works for R3. If you gave me 4 vectors in R5, I could produce a 5th vector in R5, which is the mathematical analog of the cross product, but we're not doing that in this class. If you're curious about that when we get to determinants and or projections onto subspaces, ask me then. For the moment, cross products only work in R3. As if you're given 2 vectors, those 2 vectors better be in R3. We have that the cross product of 2 vectors is orthogonal to u and orthogonal to v, which is cool, useful. We have that the cross product of u with v does not equal the cross product of v with u unless u cross v is the 0 vector. So cross product actually cares about the order. And another way in which the cross product cares is if I compute u cross v, that's a vector, right? So I could say, well, let's cross product this vector with something. So that's a vector in R3. Let's cross product with another vector in R3. This does not equal what you get if you first cross product v with w and then cross product with u. So cross products are more fiddly than dot products, but they are useful, and certainly in physics you need them. So we're going to spend some time talking about the cross product. So let's start with an example. So example, consider the plane with vector equation x is equal to 2, 1, 3 plus all linear combinations of the vector 1, 1, 1 and the vector 2, 1, 4. So we take all linear combinations of these 2 vectors, which is a plane through the origin, and then we rigidly translate that plane through the origin so that we have a plane parallel to the first plane, but goes through the point with Cartesian coordinates 2, 1, 3. And you're asked to find the scalar equation for this plane. So that means they're asking you for n1 x1 plus n2 x2 plus n3 x3 equals d. All right, so you need a scalar equation. So this means I need, what do I need if I'm going to write this down? A normal to the plane. And what else do I need? A point on the plane. Right? So the normal on the plane, there are infinitely many planes that have the same normal. To select one of those infinitely many planes, you need a single point. The moment you say that the plane has this normal and goes through this point, you've committed to a particular plane. So do we easily have a point on the plane? Yes. So the point with Cartesian coordinates 2, 1, 3 is on the plane, or in the plane, whatever you want. So the normal, so I know that I have the two vectors. So the vector 1, 1, 1 is tangent to the plane, and the vector 2, 1, 4 is tangent to the plane. Because what I did when I wrote this vector equation is I looked at all linear combinations of these two vectors. So I had those two vectors, all linear combinations went through the origin. All linear combinations of this was a plane through the origin, and then I rigidly translated it. So this vector has the same direction as would lie in the plane if you translated it by that. And this vector would lie in the plane if you translated it by that. So we have two vectors in the plane. So what do we know about the normal vector compared to these two vectors? It has to be perpendicular or orthogonal to those two vectors. So I seek a vector n that is orthogonal to 1, 1, 1 and to 2, 1, 4. Now, if you did not know about cross products, you could still solve this problem. You would have that n1 plus n2 plus n3 has to equal 0, and 2n1 plus n2 plus 4n3 equals 0, and you would find a solution. Actually, you'd find infinitely many solutions because the normal vector can have any length, and it can be flipped by direction. So you could do this without the cross product. So if you just had like a meltdown and you didn't know about the cross product, or you forgot about the cross product, you could still do this problem. Yes?
Where did you get those equations from?
Because I'm looking for a vector n, n1, n2, n3. And I want this to be orthogonal to 1, 1, 1. That's this equation. I took the dot product of this with the vector 1, 1, 1. And I asked that that dot product be 0. And then I asked that it also be orthogonal to 2, 1, 4. That's the second equation. Here I have two equations, three unknowns. I'm going to have infinitely many solutions. That one free parameter is going to just be I can put any multiplier other than 0 in front of n and still have something orthogonal to the plane. It just might be longer, shorter, flipped direction. But really, I just want to compute the cross product, 2, 1, 4. And that cross product is 3 minus 2, 1. And now that I have that, I can write down my equation, 3x1 minus 2x2 plus x3 equals yes?
You got 3
Okay, so the question is where did the rabbit come from that I just pulled out of the hat? I will show you in a moment. Right now I'm just asking you to believe me that it's useful. The question was where did that come from? And the answer is I'll show you in just a moment. So this is n. How do I get the right-hand side? I dot product n with what? The point. So I take the dot product of n, p, and so that is 6. So here what I did was I expanded out that n dot product, the position vector for x minus the position vector for the point must always be 0. If you unpack that, this is the left-hand side, and that is the right-hand side. Okay, so now let's get to the serious question of how did I compute that cross product? Okay, so where did that vector come from? Where did the entries for n come from? Yes. Sorry, what? That's n dot p. So the position vector for this point is 2, 1, 3. So this is the point. This is the position vector for that point. And so when I took the dot product of the normal with that position vector, I got 6. And the reason I did that was because of what we did on Monday about scalar equations for planes and realizing that that's this. Okay, so 3, you're absolutely right. Let's just do this correctly. Okay, so this is the normal. This is the position vector. This is 6 minus 2 plus 3, which is also known as 7. Thank you. Yes? Sorry, what? Is the question, where did this come from? Okay. This is the normal vector. 3 minus 2 minus 1. And now we compute the dot product, and we get 6 minus 5 is 1, which is what I have in my notes. And you can then check. So once you get this, you should check that your point is actually on your line. So here I would have had 3 times 2 is 6, minus 2 is 4, minus. And I would have had another. So this is the value of always double checking your work. When I plug this point in, I get 6 minus 2 minus 3 is 1. And if I had tried to plug my point in, I would have realized that the first thing I'd written was wrong. So thank you. Okay, so now we're at the question of 1, 1, 1, cross product, 2, 1, 4. Why does this equal 3 minus 2, 1? There we go. So first of all, we can check. So we can check that 1, 1, 1 dot product 3 minus 2 minus 1 is 0, and that's true. And we can check 2, 1, 4. dot product 3 minus 2 minus 1 is 6 minus 2 minus 4 is 0. So certainly this thing is orthogonal to those two vectors, but that doesn't help us actually find it. So to find the cross product, what we do is we write the following system. We put the first vector in the first row. We put the second vector in the second row. So this is just a way of remembering a complicated formula. And we get that 1, 1, 1 cross 2, 1, 4 is something times E1 plus something times E2 plus something times the vector E3. And what we do here is we now compute the difference. We compute two cross products in here. So to get the thing that multiplies E1, you block out this column and you go 4 times 1, 1 times 4 minus 1 times 1. So this is 4 minus 1. We have a minus sign here. We then multiply E2. We block out this column and we go 1 times 4 minus 2 times 1. It's 4 minus 2. And then for E3, we block out this column and we go 1 times 1 minus 2 times 1 is minus 1. So this is 3E1. 4 minus 2 is 2. Then we have a minus, so minus 2E2 minus E3. That is 3 times 1, 0, 0 minus 2 times 0, 1, 0 minus 1 times 0, 0, 1, which is 3 minus 2 minus 1. So when you get more comfortable writing computing cross products, you're going to write this down on the corner of your paper, and then you're going to write this equals this. This is one of the few formulas that at this point in your life you're going to have to just memorize. When you get a little bit further in math, you'll understand why this is how one would define a cross product. But for this moment, you're going to have to simply memorize the formula, which is something I hate to tell people, because I went into mathematics so I could avoid memorizing. In general, U cross V, U1, U2, U3, cross V1, V2, V3. The first entry is U2 minus V3 minus U3 times V2. The second entry is U3 times V1 minus U1 times V3. And the third entry is U1 times V2 minus U2 times V1. So this is in general. So we can check some simple things. So first of all, U cross U. So that's U1, U2, U3, cross product U1, U2, U3. For the first entry of the cross product, you do this times this minus this times that, and what do you get? 0. For the second entry of the cross product, you do this times this minus this times that, and you get 0. And for the third entry, this times this minus this times that, and you get 0. So in general, a vector crossed with itself is the 0 vector. Now, let's see about the, we've got u cross v written down. We can write down v cross u. So that would be v1, v2, v3, cross producted u1, u2, u3. So the first entry would be this times this minus this times that. So the first entry is v2 u3 minus v3 u2. The second entry, this times that minus this times that. v3 u1 minus v1 u3. The third entry is this times this minus this times that. So that's v1 u2 minus v2 u1. How is, so here I've got v cross u, and here I have u cross v. How are they related? It's the negative. So this is equal to the negative of u2 v3 minus u3 v2, u3 v1 minus u1 v3, u1 v2 minus u2 v1, which is u cross v. And now, as a last one, let's just check the orthogonality. So let's compute u dot producted with u cross v. So that is first component of u times first component of the cross product. Second component of u times second component of the cross product, and so on. So u1 times u2 v3 minus u3 v2 plus u2 times u3 v1 minus u1 v3 plus u3 times u1 v2 minus u2 v1. We would like this to equal what? 0. So if I'm not lying, this equals 0. So let's look at this term. u1, u2, v3. Where does that get knocked out? In the second term, I have u2, u1, v3. So that's gone. Here I have u1, u3, v2 with a minus sign. Where does that get knocked out? Third term. And then there's one term left, which is this term, u2, u3, v1, and that gets knocked out right here. You can check, make sure you understand this calculation by checking that it works for v2.